Now in this lecture, let's answer two questions. In the first question, we'll find out the area of this trapezoid, ABCD. And in the second question, we'll find out the area of this quadrilateral ABCD using two different methods. So we start with the first question. In the drawing, we have trapezoid ABCD that blocks this circle, or this circle is inscribed by trapezoid ABCD. Side AD equals to 41 units in its length, side CB also equals to 41 units in its length, side AB equals to 50 units, and our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD. In trapezoid ABCD we have two parallel sides, DC is parallel to AB. The two parallel sides DC and AB are defined as the bases of this trapezoid ABCD. And the area of this trapezoid ABCD is equal to the sum of its two parallel bases. If we define the base DC as A and the base AB as B, that is to say the base DC equals to A units in its length and the base AB equals to B units in its length, then the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. Here, the height edge creates 90 degrees with the base DC, and the height edge also creates 90 degrees with the base AB. So, repeat again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. So first of all, we'll implement rule 2 in our drawing. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common extreme point to a circle are equal. In the drawing, we have a circle. This is the common extreme point, point P. From this common extreme point, point P, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. One code in our drawing. If we focus on this common extreme point, point D, from this common extreme point, point D, we have two tangents to this circle, but first of all, we define the point of tendency of tangent DA in this circle. This point is point E. Likewise, we define the point of tendency of tangent DC in this circle. This point is point F. We define the point of tendency of tangent CB with this circle. This point is point G. We define the point of tendency of tangent AB with this circle. This point is point H. So we focus on this. Common extreme point, point D. From this common extreme point, point D, we have two tangents to this circle, tangent DE and tangent DF, and according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if you define the length of tangent DE as A, then the length of tangent DF must be also equal to A because they are equal to each other according to rule 2. Likewise, we will focus on this common extreme point, point D. From this common extreme point, we will focus on this common extreme point, point C. For this common extreme point, point C, we have two tangents to this circle, tangent CF and tangent CG. And according to rule 2, they are equal to each other. That is to say, CF equals to CG. So if we define the length of tangent CF as B, then the length of tangent CG must be also equal to B because they are equal to each other according to rule 2. Likewise, we'll focus on this current example point A. For this current example point A, we have two tangents to this circle, tangent AE and tangent AH. And according to rule 2, they are equal to each other. That is to say, AE equals to AH. So if we define the length of tangent AE as C, then the length of tangent AH must be also equal to C because they are equal to each other according to rule 2. And finally, we focus on this kind of example point B. From this kind of example point B, we have two tangents to this circle, tangent BG and tangent BH. And according to rule 2, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BG as D, that is to say, tangent BG equals to D unit in its length, then tangent BH must be also equal to D because they are equal to each other according to rule 2. What is the length of side DA plus the opposite side CB? DA plus CB. DA plus CB in total equals to A plus B plus C plus D. So DA plus CB equals to A plus B plus C plus D. What is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if you found out that DC plus AB also equals to A plus B plus C plus D, and because of the fact that those two expressions, the sum of those two expressions is equals to A, or those two expressions are equal both to A plus B plus C plus D, it means that they are equal to each other. So you know, if you found out that DA plus CB equals to DC plus AB. Those both two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. DA is 41. Plus CB is also 41. And it is equal to DC is the missing side, so leave it as it is, plus AB equals to 50, according to what is given in the question. So in total, we have found out that 41 plus 41 equals to DC plus 50. 41 plus 41 is 82, so 82 equals to DC plus 50. Here we will subtract 50 for this equation, and we get that DC equals to 82 minus 50 is 32. So DC equals to 32 units in its length. This is side DC. That is equals to 32 units in its length. So I write it down. DC equals to 32 units in its length. In the next step, we will do a construction. That is to say, from point C, we will do perpendicular on AB. Again, from point C, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AB. This point is point J. Likewise, we will do another construction, that is to say, from point D, we will do perpendicular on AB. Again, from point B, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. We know that ABCD is a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. In trapezoid ABCD, side DC is parallel to the opposite side AB. Again, DC is parallel to AB. Those two angles, they are both defined as one-sided interangles, and they are located between the parallel lines DC and AB. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. So I put quickly on Rule 17. According to Rule 17, the sum of one-sided interangles that are located between parallel lines is equal to 180 degrees. In the drawing, we have line A that is parallel to line B. Those two angles, alpha and beta, are defined as one-sided interangles. And because of the fact that line A is parallel to line B, the sum of those two one-sided interangles is equal to 180 degrees. That is to say, alpha plus beta equals to 180 degrees. So we can actually implement Rule 17 in our drawing. Why? Because in our drawing, we know that DC is parallel to AB, and those two one-sided interangles are located between the parallel lines DC and AB, and therefore the sum of those two one-sided interangles must be equal to 180 degrees. So 90 degrees plus the size of this angle DCJ, in total they must be equal to 180 degrees according to Rule 17. So I write it down. 90 degrees, this angle is right angle, plus this is angle DCJ. In total, the sum of those two one-sided triangles must be equal to 180 degrees according to Rule 17. So here we subtract 90 degrees from this equation, and finally we get that the size of the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. So okay, this is the missing angle DCJ that is equal to 90 degrees in its size. Likewise, the sum of those two one-sided triangles that are located between the parallel lines DC and AB is equal to 180 degrees according to rule 17. So I write down this angle, this is a right angle, 90 degrees, plus the size of this missing angle, that is a triangle CDN. In total, the sum of those two one-sided triangles must be equal to 180 degrees because they are located between the parallel lines DC and AB, according to rule 17. So 90 degrees plus the size of the missing angle CDN in total must be equal to 180 degrees according to rule 17. Here we subtract 90 degrees from this equation and finally get that the size of the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. So if you find out that the size of this missing angle CDN is equal to 90 degrees in its size. So in this quadrilateral CD and J, in this big quadrilateral CD and J, we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must make this rectangle in front of square. So we have to quadrilateral CD and J as a rectangle because it has 4 right angles. So I write it down. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DC and J, side DC must be equal to the opposite side NJ. But DC is 42, therefore the opposite side NJ must be also equal to 32 units in its length. Likewise, according to the same rule, in the same rectangle DC and J, side CJ must be equal to the opposite side DN. So CJ equals to DN. So in the drawing we have 2 right angles, 2 right angles. This is triangle CJB, that is a right angle. This is triangle DNA, that is also a right angle. Those 2 right angles can go into each other according to side rule. That is to say, those 2 sides that are the hypotenuse of those 2 right angles are both equal to 41 units and therefore they are equal to each other. Those 2 sides are also equal to each other, according to the rule that the opposite sides of a rectangle are equal to each other. And finally, those 2 sides are also equal to each other. I'll explain why those 2 sides are equal to each other. So I copied these right angles in a new page and I proved that those 2 sides are also equal to each other. So finally, this is the right angle DNA, this is the right angle CJB, that is according to the original drawing. We defined the length of the hypotenuse DA is y. In this right angle DNA, therefore the length of the hypotenuse CBJ must be also equal to y because they are equal to each other. Both of them are equal to 41, therefore they are equal to each other. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, side CJ equals to side DN. So we define the length of side CJ as x, and therefore DN must be also equal to x because they are equal to each other. And finally, those 2 sides are also equal to each other. Why those 2 sides are equal to each other? Here we implemented the Pythagoras theorem on this rectangle DNA. according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in this right triangle DNA, dA squared, that is the square of the hypotenuse, equals to dN squared plus NA squared. So y squared equals to x squared plus NA squared. Again, y squared equals to x squared plus NA squared. Here we subtract x squared from the equation and find out that y squared minus x squared equals to an squared. Here we took out this equation and found out that the missing side an equals to the square root of y squared minus x squared. We repeated on the same process here. We implemented the Pythagoras theorem on this right triangle CJB. According to the Pythagoras theorem, in this right triangle CJB, y squared equals to x squared plus jb squared. Again, y squared equals to x squared plus jb squared. Here we subtract x squared from the equation and find out that jb squared equals to y squared minus x squared. So here we took out this equation and found out that jb equals to the square root of y squared minus x squared. So jb equals to the square root of y squared minus x squared, and an also equals to the square root of y squared minus x squared. And because of the fact that jb and an are both equal to the square root of y squared minus x squared, it means that they are equal to each other. That is to say, an equals to jb. An equals to jb. So actually found out that those two right triangles can go into each other according to side rule. Okay. So after that, she found out that the right triangle CJB can warrant this is the sign of congruent to the right triangle DNA according to side rule. And for the fact that those two right triangles can go into each other, we derive that the following that AN in the right triangle DNA is equal to JB in the right triangle CJB. So AN equals to JB. AN equals to JB according to the rule that corresponding sides of congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides must be also equal to each other. So, if we define the length of AN as x, then the length of JB must be also equal to x because they are equal to each other. So what is the length of AB? AB in total equals to 50 degrees from one side, but from the other side AB also equals to AN, that is x, plus NJ, that is 32, plus JB, that is x. So in total we found out that AB equals to 50 and it is equal to x plus 32. So from this equation we derive that 50 equals to 2x plus 32. Here we subtract 32 from this equation. Finally we get that 2x equals to 50 minus 32 is 18. So 2x equals to 18. Here we divide this equation by 2 and finally we get that x equals to 18 over 2, that is 9. So x equals to 9 units in its length. AN that equals to x equals to 9 units. And JB that is also equals to x equals to 9 units in its length. In the next step, I'll copy the right triangle CJB in a new page, and we will implement the Pythagoras theorem on this right triangle CJB. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle CJB that are coming from the original domain. In this right triangle CJB, according to the Pythagoras theorem, CB squared, that is the score they are produced, equals to CJ squared plus JB squared. So I write it down. CB squared, that is the score they are produced, equals to CJ squared plus JB squared. CB equals to 41, therefore CB squared is 41 squared, that is 1681, and it is equals to CJ squared. CJ is the missing sign, so we'll leave this it is. It is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, it is 81. So in total, we actually found out that 1681 equals to CJ squared plus 81. Here we subtract 81 from this equation, and finally we get that 1681 minus 81 is 1600 equals to CJ squared. So CJ squared equals to 1600. Here we take a root out of this equation, and finally we get that the missing side CJ equals to the square root of 1600, that is 40. So okay, this is the missing side CJ, that equals to 40 units in its length. Our task is to find out the area of this trapezoid ABCD. In the beginning of the lecture, I explained to you that the area of a trapezoid equals to the sum of its two parallel bases times the height over 2. Therefore, the area of this trapezoid ABCD will be equal to the sum of its two parallel bases. The sum of its, the two parallel bases are DC and AB. So it is DC plus AB times the height over 2. The height is CJ because it creates 90 degrees with the base AB, also creates 90 degrees with the other base CD. So the height is CJ divided by 2. Okay, again, we shall find out that the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that is to say DC plus AB times the height, that is CJ over 2. DC equals to 32 units in its length, plus AB is 50, according to what is given in the question, times the height CJ. We just right now found out that the height CJ equals to 40 units in its length, divided by 2. So today we found out that the area of this trapezoid ABCD is equal to 32 plus 50 times 40 over 2. 32 plus 50 is 82, and 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20, that is 1640 square units in its size. And again, we found out that the area that we are looking for in this question, that is the area of this trapezoid ABCD, is equal to 1640 square units in its size. So finish with the first question. In the next step, I will present to you the second question, and we will solve the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So, in the moment we have quadrilateral ABCD. This is side AB, that is equals to 10 units in its length. This is side DC, that is equals to 25 units in its length. This is angle ABC, that is a right angle. This is angle ADC, that is also a right angle. This is angle BCD, that is equals to 45 degrees in size. Again, our task is to find out the area of this quadrilateral ABCD. So, first of all, we'll do a construction, that is to say from this point B, we'll do perpendicular on DC. Again, from point B, we'll do perpendicular on DC. So actually this angle equals to 90 degrees, and this angle must be equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point D, from point B, and DC. This point is point N. In the next step, we will do another construction. That is to say, from this point A, we will do perpendicular on BN. Again, from point A, we will do perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in BM. This point is point M. By doing this construction, we can do the quadrilateral AM and D. In quadrilateral AM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle, the total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4-piece angle must be equal to 90 degrees in its size. So in quadrilateral AM and D, we have 4 right angles, and therefore, according to rule 5, quadrilateral AM DN is a rectangle, because it is 4 right angles. So as is known, this is quadrilateral AM DN, it is a rectangle according to rule 5. But we also, before that, we define the length of side AM as A. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle AM DN, this rectangle AM DN, side AM must be equal to the opposite side DN, but AM is A, therefore DN must be also equal to A units in its length. So DN equals to A units in its length. In the next step, we will focus on this right big triangle B and C. This is the right triangle B and C. In this right triangle B and C, this right triangle B and C, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Again, 45 degrees plus 45 degrees, 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. We have the rule that states that in front of equal angles in a triangle, there are equal sides. And repeat again, in front of equal angles in a triangle, there are equal sides. So if we focus on the right triangle B and C, this is the right triangle B and C. In front of those two equal angles, we have those two sides that are also equal to each other. But side NC, what is the rule of side NC? NC equals to 25 minus 8. NC equals to 25 minus 8. So in the right triangle B and C, in front of those two equal angles, we have those two sides that are also equal to each other. But NC equals to 25 minus 8, therefore BN must be also equal to 25 minus 8 units in its length. So this is side BN. It is equals to 25 minus 8 units in its length. It is given us the question that the big angle ABC equals to 90 degrees in its size. angle NBC equals to 45 degrees in its size. So the big angle ABC minus this angle ADC, this equals to 45 degrees, will be equal to the size of the missing angle ABM. Again, the big angle ABC minus this small angle BNC must be equal to the missing angle ABN. That is to say 90 degrees minus 45 degrees is 45 degrees. So the missing angle ABM, the missing angle ABN must be equal to 45 degrees in size. So in the right small triangle ABM, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we'll focus on the right small triangle ABM. On the right small triangle ABM, in front of those two equal angles, we have those two sides that are also equal to each other. But side AM equals to A, therefore side BM must be also equal to A. So the norm BM also equals to A. So what is the length of this missing line segment MN? From the drawing it is very easy to see that MN in total equals to BN must be M. Again, BN must be M equals to MN. So I write it down. If we found out that MN equals to BN minus BM. So MN equals to BN. BN is 25 minus A. Minus BM. BM is A. So in total, MN equals to 25 minus A minus 8. That is 25 minus 2A. So MN equals to 25 minus 2A. So here, this is the missing side MN. This equals to 25 minus 2A units in its length. But in rectangle AMDN, this is rectangle AMDN, side MN must be equal to the opposite side AD, but MN is 25 minus 2A, therefore AD must be also equal to 25 minus 2A units in its length. AD equals to 25 minus 2A units in its length. In the next step, we will implement the Pythagoras theorem of this right small triangle ABM. So I'll copy the right small triangle ABM in an equation. We will implement on it the Pythagoras theorem. Here by PT is the progression from Pythagoras theorem. So actually, this is the right triangle ABM. This is according to the original drawing. In this right triangle ABM, according to the Pythagoras theorem, BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. So write it down. BA squared, that is the square of the hypotenuse, equals to BM squared plus AM squared. BA is 10, therefore BA squared is 10 squared, it is 100. And it is equals to BM squared. BM is 8, therefore BM squared is 8 squared. Plus AM squared. AM is also 8, therefore AM squared is 8 squared. 8 squared plus 8 squared is 2A squared, so in total we found out that 100 equals to 2A squared. 100 equals to 2A squared. Our task is to find out the area of this quadrangle ABCD. Actually, this is quadrangle A, B, and D. Quadrangle A, B, and D is a trapezoid. Why quadrangle A, B, and D is a trapezoid? Because we know that the opposite sides of a rectangle are parallel to each other. Again, the opposite sides of a rectangle are parallel to each other. So in rectangle AM and D, side MN is parallel to side AD. But BN, line segment BN is a straight line because angle BMN equals to 180 degrees. And we know that any angle that equals to 180 degrees inside, it is defined as a straight line. So BN is a straight line. And we know that part of the straight line BN, that is MN, is parallel to AD. So if a part of a straight line is parallel to the other straight line, then the straight line BN itself must be also parallel to AD. So BN is parallel to AD. So quadrangle A, B, and D is one pair of parallel sides. That is to say, side BN is parallel to side AD, and therefore quadrangle A, B, and D is a trapezoid. So write it down. If you found out that quadrangle A, B, and D is a trapezoid. If you found out that the quadrangle A, B, and D is a trapezoid. But what is the area of this trapezoid? Trapezoid A, B, and D. Actually, the area of trapezoid A, B, and D is equal to the sum of its two parallel sides, that is to say AD plus BN times the height AM over 2. So write it down. The area of this trapezoid A, B, and D is equal to the sum of its two parallel sides. Side BN is parallel to side AD. It's already proved. So it is BN plus AD times the height AM over 2. AM creates 90 degrees with the two parallel sides, that is to say, AM is parallel, this angle equals to 90 degrees, and this angle also equals to 90 degrees, and AM also creates 90 degrees with side AD. Therefore, AM is the height of trapezoid ABCD divided by 2. And again, we found out that the area of trapezoid AB and D in total equals to the sum of its two parallel sides, that is to say BN plus AD times the height AM over 2. BN equals to 25 minus A plus AD. AD equals to 25 minus 2A times the height AM. AM equals to A divided by 2. So in total we found out that the area of this trapezoid AB and D equals to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50. Minus A minus 2A is minus 3A times A over 2. 50 times A is 50A. Minus 3A times A is minus 3A squared divided by 2. So in total we found out that the area of trapezoid AB and D is equal to 50A minus 3A squared over 2. And again, we found out that the area of trapezoid AB and D equals to 58 minus 3A squared over 2. Our task is to find out the area of this quadrangle ABCD. So what is the area of quadrangle ABCD? From the drawings, it's very easy to see that the area of this quadrangle ABCD in total equals to the area of trapezoid AB and D plus the area of the right triangle B and C. So write it down. The area of this quadrangle ABCD in total equals to the area of this trapezoid AB and D plus the area of this right triangle B and C. But again, we should found out that the area of this quadrangle ABCD in total equals to the area of trapezoid AB and D plus the area of the right triangle B and C. But we already found out that the area of trapezoid AB and D equals to 50A minus 3A squared over 2. So the area of trapezoid ABC and D equals to 50A minus 3A squared over 2 plus the area of the right triangle B and C. What is the area of this right triangle B and C? The area of the right triangle B and C equals to the base of the right triangle B and C, that is NC, times the height, that is BN, divided by 2. And again, in total, the area of this right angle BNC equals to the base NC times the height BN over 2. So in total, the area of quadrilateral ABCD equals to 50A minus 3A squared over 2 plus NC times BN over 2. NC is 25 minus A times Bn. Bn is also 25 minus A, so it is 25 minus A squared divided by 2. So in total, we have found out that the area that we are looking for this question, that is the area of quadrilateral ABCD equals to 50A minus 3A squared plus 25 minus A squared over 2. Here we'll open the brackets of this expression and finally we get that the area of quadrilateral ABCD equals to 50A minus 3A squared plus 25 minus A squared. 25 minus A squared equals to 25 squared, that is 625, plus A squared minus 2 times 25 times 8, that is minus 58, divided by 2. 58 minus 58 is 0, so those two expressions will get cancelled. And we have minus 3A squared plus A squared is minus 2A squared. And we have also 625. So in total, we actually found out that 625 minus 2A squared over 2 is the area of quadrilateral ABCD. Is the area of this quadrilateral ABCD. And again, the area of quadrilateral ABC in total equals to 625 minus 2A squared over 2. But we have already found out that A squared equals 200. Therefore, we can substitute 2A squared in this equation by 200. We'll do it now. We get that 625 minus 2A squared. 2A squared is 100 divided by 2. So in total, the area of quadrilateral ABCD equals to 625 minus 100, that is 525 over 2. 525 over 2 is 262.5 square units in its size. So the final answer to the question is that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square units in its size. So we finish with the first method. In the next step, I'll present to you how to find out the area of this quadrilateral ABCD by using a second method. In the second method, we will do a construction. That is to say, we will extend side DA and side CB on this quadrilateral ABCD by a straight line until they touch each other. Actually, this is the attaching point. We define this point, the attaching point, as M. By doing this construction, we can do the big right triangle MCD. In the big right triangle MCD, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We focus on the big right triangle MDC. On the big right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. but DC is 25, therefore MD must be also equal to 25 units in its length. According to the rule that in front of equal angles in the triangles, there are equal sides. So MD also equals to 25 units in its length. BMC is the hypotenuse of the big right triangle MDC. So MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle, this is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the small right angle MBA, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the small right angle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AB is 10, therefore side MB must be also equal to 10 units in its length. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. So the area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of this small right triangle MBA. And again, we should find out that the area that we are looking for in this question, that is the area of quadrilateral ABCD, equals in total to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base of the triangle that is DC times the height that is DM divided by 2. And again, the area of this big right triangle MDC equals to the base of the right triangle MDC that is DC times the height that is DM over 2. Minus the area of this right small triangle MBA. The area of this right small triangle MBA equals to the base AB times the height BM over 2. And again, the area of this right small triangle MBA equals to the base AB times the height to the base BM over 2. DC is 25 times DM is also 25, so 25 squared over 2 minus the area of this small right triangle MBA. The area of this small right triangle MBA equals to the base AB, that is 10, minus the height of the base MB, that is also 10, so it is 10 squared. So in total, we found out that the area of this quadrilateral ABCD equals to 25 square minus 10 square. 25 square divided by 2, of course. 25 squared is 625, minus 10 squared is 100, divided by 2. 625 minus 100 is 525, divided by 2. 525 over 2 is 262.5 square units in size. So in both methods, we have found out that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square units in its size. So we finish with the second method of the second question. In the next step, I'll summarize the lecture. I'll start with the first question, of course. In the first question, our task was to find out the area of this trapezoid ABCD. So in the domain, we have a circle that is inscribed by trapezoid ABCD. Side DA equals to 41. Side CV also equals to 41 units in its length. Side AB equals to 50 units in its length. Again, our task is to find out the area of this big trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD. Side DC is parallel to side AB, therefore quadrilateral ABCD is a trapezoid. If we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is actually A plus B times the right edge over 2. The right edge must be 90 degrees with the two parallel bases. And again, the area of this trapezoid, or the area of the trapezoid, equals to the sum of its two parallel bases times the height over 2. And the height must be 90 degrees with the two parallel bases. So first of all, we implemented rule 2 in our drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common extra point to a circle are equal. So in the drawing, we have a circle. This is a common extra point, point P. From this common extra point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common extra point, point D, from this common extra point, point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length of DE as A, then the length of DF must be also equal to A, because they are equal to each other according to rule 2. Likewise, if we focus on this common extra point, point C, from this common extra point, point C, we have two tangents to this circle, tangent CF and tangent CG. And according to rule 2, they are equal to each other. That is to say, CF equals to CG. So if we define the length of CF as B, then the length of CG must be also equal to B, because they are equal to each other according to rule 2. Likewise, if we focus on this common extra point, point A, from this common extra point, point A, we have two tangents to this circle, tangent AE and tangent AE edge. And according to rule 2, they are equal to each other. That is to say, AE equals to AH. So if we define the length of tangent AE as C, then the length of tangent AH must be equal to C, because they are equal to each other according to rule 2. And finally, if we focus on this common extra point, point D, point B, from this common extra point, point B, we have two tangents to this circle, tangent BH and tangent BG. And according to rule 2, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BG as D, then the length of tangent BH must be also equal to B because must be also equal to D because they are equal to each other according to rule 2. So what is the length of side DA plus side CB? DA plus CB in total equals to A plus B plus C plus D. Likewise, what is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if you found out that both those two expressions, they are both equal to A plus B plus C plus D, therefore they must be equal to each other in the length. So in total, DA plus CB must be equals to DC plus AB. DA is 41, CB is also 41, DC is the missing side, and AB is 50. 41 plus 41 is 82, equals to DC plus 50. Here we subtract 50 from the equation and find out that 82 minus 50 is 32, so DC equals to 32 units in its length. This is the missing side DC, this equals to 32 units in its length. In the next step, we did a construction, that is to say, from point 0 to perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. In the next step, we did another construction, that is to say, from point D, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point M. We know that ABCD is a trapezoid. In trapezoid ABCD, side DC is parallel to side AB. So those two angles are defined as one-sided interangles, and they are located between the parallel DC and AB. Therefore, according to Rule 17, the sum of two one-sided interangles that are located between parallel lines is equal to 180 degrees. So the sum of those two one-sided interangles equals to 180 degrees. This is a right angle. So 90 degrees plus this missing angle, in total it must be equal to 180 degrees according to Rule 17. Again, 90 degrees plus the missing angle CDN, in total it must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from this equation, and find out that the missing angle CDN is equal to 90 degrees in its size. Likewise, those two angles are defined as one-sided interangles, and are located between the same parallel lines DC and AB. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. But this is a right angle, so 90 degrees plus the size of this missing angle, that is actually angle DCJ. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. So 90 degrees plus the missing angle DCJ must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from this equation, we found out that the missing angle DCJ equals to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle DCJ, that is equals to 90 degrees in its size. So in quadrilateral DCJN, we have four right angles. But again, in quadrilateral DCJN, we have four right angles, and therefore according to Rule 5, quadrilateral DCJN is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, according to the sum rule, in the sum rectangle DCJN, side DN must be equal to the opposite side DJ. So those two sides are equal to each other. If you focus on those two right angles, in those two right angles, the hypotenuse DA equals to the hypotenuse CB, they are both equal to 41, and therefore they are equal to each other. Those two sides are also equal to each other, according to the rule that the opposite sides of the rectangle are equal to each other. And those two sides are also equal to each other. Actually proved that those two sides are also equal to each other. Actually copied those two right angles in a new page and proved that those two sides are also equal to each other. Those are the two right angles that are copied from the original domain. We have to prove that AN equals to JB. In the right angle DNA, y squared equals to x squared plus an squared. Again, y squared equals to x squared plus an squared. Here we subtract the x squared from this equation. From this equation, we find out that an squared equals to y squared minus x squared. Here we took root out of this equation and find out that the missing side an equals to the square root of y squared minus x squared. Likewise, we repeated on the same process in this right angle CJB. In this right angle CJB, y squared equals to x squared plus jb squared. Again, y squared equals to x squared plus jb squared. Here we subtract x squared from the equation and find out that jb squared equals to y squared minus x squared. Here we took root out of this equation and find out that the missing side jb also equals to the square root of y squared minus x squared. So AN equals to the square root of y squared minus x squared, and JB also equals to the square root of y squared minus x squared. And because of the fact that those two sides are both equal to the same expression, they must be equal to each other in their lengths. That is to say, AN equals to JB. And therefore, those two right angles can go into each other according to side rule. That is to say, those two sides are both equal to y, therefore they are equal to each other. In addition, those two sides are both equal to x, and therefore they are equal to each other. And finally, side AN equals to side JB. Therefore, those two right angles can go into each other according to side rule. Again, if you found out that the right angle CJB can go, this is the side of congruent, to the right angle DNA according to side rule. And from the fact that those two right angles can go into each other, we derive that the side AN equals to side JB. Side AN equals to side JB. AN equals to JB according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AN and JB, must be also equal to each other in their lengths. If AN equals to JB, it means that if AN is x, then JB must be also equal to x. AB in total is 50 from one side, but from the other side, again AB in total is 50 from one side, but from the other side, AB also equals to AN, that is x, plus NJ, that is 32, plus JB, that is x. So in total, AB also equals to 2x plus 32. Again, from one side, AB equals to 50, but from the other side, AB also equals to x plus 32. That is to say, 50 equals to 2x plus 32. If subtracting 32 from this equation, found out that 2x equals to 50 minus 32 is 18. Here we divided this equation by 2 and found out that x equals to 9 units is there. So this is side AN, that equals to x, and x equals to 9. This is side JB, that equals to x, and x equals to 9. In the next step, I copied the right angle CJB in a new page, and we implemented the Pythagoras on this right angle CJB. This is the right angle CJB that comes from the original domain. So in this right triangle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681, and it equals to CJ squared. CJ is the missing side, so we need to see this, so it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total we found out that 1681 equals to CJ squared plus 81. If subtracted 81 from this equation, and finally found out that 1681 minus 81 is 1600, so 1600 equals to CJ squared. If we took out of this equation, we found out that CJ equals to the square root of 1600, that is 40. So this is side CJ, this equals to 40 units in its length. CJ is also actually the height of the trapezoid ABCD. Our test is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two parallel sides, that is to say DC plus AB, times the height CJ over 2. Then again, the area of trapezoid ABCD in total equals to the sum of its two parallel sides, that is DC plus AB, times the height CJ over 2. DC is 32, AB is 50, CJ is 40. And again, DC is 32, AB is 50, and CJ is 40, divided by 2. 32 plus 50 is 82, and 20 over 2 is 20. So in total, the area of this trapezoid ABCD equals to 82 times 20, it is 82 times 20, that is 1640 square units in size. But again, if we found out that the area of this trapezoid ABCD equals to 1640 square units in size. So we finish with the first question. In the next step, I presented to you the second question, and we solved the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. This is angle ABC, that is right angle. This is angle ADC, that is also right angle. This is angle BCD. This equals to 45 degrees inside. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we did a construction. That is to say, from point B we do perpendicular on DC. Again, from point B we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tension point of the perpendicular from point B and DC, this point N. In the next step we did another construction, that is to say, from point A we do perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the starting point of the perpendicular from point A and BN, this point is point M. By doing this construction, we get the quadrilateral AM and D. Inside quadrilateral AM and D, we have 1, 2 free right angles. The sum of free right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 pieces again must be equal to 90 degrees in its size. Therefore, quadrilateral AM and D is a rectangle because it has 4 right angles. But we also know, so we define the left of side AM as A, and we know that the opposite sides of rectangle are equal to each other. So in rectangle AM and D, side AM is equal to the opposite side DN. But AM is A, according to our definition, therefore DN must be also equal to A units in its length. In the next step, we focus on this right triangle B and C. In the right triangle B and C, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We also have the rule that in front of equal sides, in front of equal angles in the triangle, there are equal sides. So in front of those two, in the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other. But NC is 25 minus 8, therefore BN must be also equal to 25 minus 8 units in its length. So this is the angle ABC. This equals to 90 degrees. The smaller angle NBC equals to 45 degrees, and therefore this piece angle must be equal to 90 degrees minus 45 degrees, and this 45 degrees. So in the right triangle BMA, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this angle must be equal to 45 degrees in size. So in the small right triangle BMA, in front of those two equal angles, we have those two sides that must be equal to each other, but that must be also equal to each other in their lengths. But AM is A, therefore BM must be also equal to A. So MN in total equals to BM, that is 25 minus A, minus BM, that is A. So again, MN equals to BM, BN minus BM. So MN in total equals to BN, that is 25 minus A, minus BM, that is A. So in total, MN equals to 25 minus A, that is 25 minus 2A. So this is side AMN, that is equals to 25 minus 2 units in its length. But we know that the opposite sides of the rectangle are equal to each other. So in the rectangle AM and D, side MN must be equal to the opposite side AD. But MN is 25 minus 2A, therefore AD must be also equal to 25 minus 2 units in its length. In the next step, we implemented the Pythagoras theorem on this right triangle ABM. So copy the right triangle ABM in the new page and we implemented only the Pythagoras theorem. This is the right triangle ABM, that is the common from the original drawing. This right triangle ABM, BA square equals to BM square plus AM square. BA is 10, therefore BA square is 10 square, that is 100, and this equals to BM square. BM is 8, therefore BM square is A square, plus AM square. AM is also 8, therefore AM square is A square. So in total, we have found out that 100 equals to A square plus A square, that is 2A square. So 100 equals to 2A square. This is quadrilateral A, B, and D. Quadrilateral A, B, and D is a trapezoid. Why? Because first of all, in the rectangle AM and D, side MN is parallel to the opposite side AD. But MN is part of the straight line BN. Why BN is a straight line? Because again, BMN is 180 degrees. Again, MN is part of the straight line BN. So if a part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to another straight line. So in quadrilateral A, B, and D, side BN is parallel to the opposite side AD, and therefore quadrilateral A, B, and D is a trapezoid because a trapezoid is a quadrilateral with one pair of parallel sides. So quadrilateral A, B, and D is a trapezoid because it has one pair of parallel sides. BN is parallel to AD. So in trapezoid A, B, and D, the area of trapezoid A, B, and D equals to the sum of its two parallel sides, that is BN plus AD times the height MA over 2. In the end, the area of trapezoid ABCD equals to the sum of its two parallel sides, that is actually BN plus AD times the height AM over 2. BN is 25 minus 2, 25 plus 2A, 25 minus 2A, AD is 20, again, BN is 25 minus A, AD is 25 minus 2A, AM is A, divided by 2. Again, BN is 25 minus A, plus AD is 25 minus 2A, times AM is A over 2. We have 25 plus 25 is 50, and minus 8 minus 2A minus 3A times A over 2. 50 times A is 58, and minus 3A times A is minus 3A square over 2. So in total, we found out that the area of trapezoid A, B, and D equals to 58 minus 3A square over 2. Okay, again, we found out that the area of this trapezoid A, B, and D In total, it is equals to 58 minus 3 squared over 2. Our test is to find out the area of this quadrilateral, quadrilateral A, B, and D. So what is the area of quadrilateral A, B, and D? From the drawing, it is very easy to see that the area of this quadrilateral A, B, and D in total equals to the area of trapezoid A, B, and D plus the area of this right triangle B and C. Repeat again, the area of this quadrilateral A, B, C, and D in total equals to the area of trapezoid A, B, and D plus the area of the right triangle B and C. We already found out that the area of this trapezoid A, B, and D equals to 58 minus 3 squared over 2 plus the area of the right triangle B and C. The area of this right triangle B and C equals to the base and C times the height and B over 2. The base and C times the height B n over 2. So the area of quadrilateral ABCD equals to 58 minus 3 squared. NC is 25 minus A, and Bn is also 25 minus A. So NC times Bn is 25 minus A squared divided by 2. We open the brackets here, if you found out that 58 minus 3 squared and 25 minus A squared equals to 25 squared, that is 625 plus A squared minus 2 times 25 times 8, that is minus 58 divided by 2. 58 minus 58 is 0, so those expressions will get cancelled. And you have told me if minus 3 squared plus A squared is minus 2A squared plus 625 divided by 2. So if you found out that 625 minus 2A squared over 2 is the area of quadrilateral ABCD. But we already found out that 2A squared equals to 100. Therefore, we can substitute 2A squared here by 100. We did it, and we found out that 625 minus 2A squared is 100 over 2. 625 minus 100 is 525 over 2. So in total, if you found out that the area of this quadrilateral ABCD is equals to 525 over 2, that is 262.5 square meters in size. We finish with the first method. In the next step, I presented to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we did the construction, that is to say, we extended side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. We define their touching point, this point is point M. By doing this construction, we can deduce the right triangle MDC. The right triangle MDC, this angle equals to 9 degrees, this angle equals to 45 degrees, and therefore this furthest angle must be equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other on their lengths. But DC is 25, therefore MD must be also equal to 25 units in its length. MC is the hypotenuse of the right triangle MDC, therefore MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of MC at point B, we have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 2. Therefore, this missing angle must be equal to 90 degrees in size. So in the small right triangle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this furthest angle must be equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the small right triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But AB is 10, according to what is given to the question, therefore BM must be also equal to 10. What is the area of this quadrilateral ABCD? From the domain, it is very easy to say that the area of this quadrilateral ABCD in total equals to the area of the big right triangle MDC minus the area of the small right triangle MBA. Again, the area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. What is the area of the big rectangle MDC? The area of the big rectangle MDC equals to the base DC times the height DM over 2. Again, the area of the rectangle MDC total equals to the base DC times the height DM over 2. Minus the area of this small rectangle MBA. The area of the small rectangle MBA equals to the base AB times the height BM over 2. Again, the area of the small rectangle MBA equals to the base AB times the height BM over 2. DC is 25, DM is also 25, which is 25 square, minus AB is 10, and BM is also 10, so it is 10 square. So we have the area of quadrilateral ABC total equals to 25 square, minus 10 square over 2. 25 square is 625, minus 10 square is 100 divided by 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square meters in size. So in both methods, we actually found out that the area that we're looking for in this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square meters in size. Okay, thank you very much.